रो मु शेयर कर दे विजुअल है कि तुमको स्लाइड देखा होची
आगे देखा
पीडीएफ टा देखाला अल्फा डीके देखा होची हेलो
अल्प टिके झापसा देखा होची
हाँ एटा पीडीएफ टा तो सेट में ठीक अछि तो लेट मी स्टार्ट एक्चुअली व्हाट योर as per the syllabus this is alpha decay okay so in this actually that you have to particularly you have to read here let me show tell you alpha beta gamma decay then gamos theory of alpha decay okay then okay see here so what is that alpha decay actually you know that alpha beta gamma are the part simple the particles or the part decay that in the BSc classes you may have read these are the part simple the radioactive decay the radioactive rays which are get emitted from the nucleus due to the part radioactive the radioactive process okay so the alpha decay is one of the part earliest nuclear process and a typical type of radioactivity in heavy nuclei okay and a Coulomb barrier of more than 20 MeV is experienced by an alpha particle when it collides with a part heavy nuclear like uranium, whereas alpha particle produced by uranium have energies less than part 5 eV. So in this actually we have to first understand actually what is that actually we have to talk about the part range of the alpha particle, then the energy of the part actually part this just neutral law, then gamma zero alpha decay. These are all things are part there. So before so first of all let me talk about actually part alpha decay. What is that alpha decay? Now the process of disintegration in which that alpha particles are get emitted from the part radioactive nucleus okay that is called the part alpha decay okay so in this context you have to particularly you have to read actually what is that alpha decay and that how this alpha decay actually created in a part nuclear reaction or that is called the part range of the part alpha particle. So in discussion of the part range of the alpha particle is released by part naturally occurring radioactive elements are quickly absorbed by the part matter and actually they are part very less penetrate moving with the part low velocity okay but high ionizing power okay so they are simply able to pass through the thin foil made up of mica or aluminum as well as the thin paper. They can only get through the top few layer of such material. As they go through off stop they lose energy and after a given distance in matter the mono energetic particle lose all of their part energy by subsequent collision. The term range refers to the part maximum distance of a particle in a substance can go before losing all of its energy. That means, so before reaching to a part maximum distances, so if it will lose the part energies, so the maximum distance up to which the alpha particle can move through a part material that is called the part range. Okay. Now we'll go to the part range energy relationship in terms of velocity. Actually, so when this is actually first observed by the part Rutherford, and in this mathematical relationship between the part measured values of the range and the energy of the alpha particle, we find that R is equal to alpha a to the power 3/2, and this is a part simple empirical relationship. Okay, means a part theoretical relationship that is valid limited up to a part range is about 3 to 7 MeV, and that is known as part Giger's law. Okay, so if V is a part velocity of the alpha particle, then I can say R is the range of the part particle that is part BVQ, and where V is a part simple constant, and that the range of the part. So in case of a solid, the range of the part alpha particle is found to be part this constant times a to the power 1/2 by rho. A is the part mass number of the part nucleus, and then rho is the part density. Okay, and for higher low energy, more appropriate relationship can be given by that is R is per V to the power 4 actually, and where R is proportional to V to the power 3/2 actually. Okay, so then this is the part range and velocity relationship that you may get a question what is alpha decay. So what do you mean the range of the alpha particle? establish a relationship between the range and the velocity of the alpha particle. Okay. Then the Giger neutral law is part. So this Giger and part neutral had discovered an empirical relationship between the decay constant of a naturally occurring radioactive element and the range of the alpha particle. And Giger neutral law, which may be written as a part, that is law logarithm of the lambda, that is lambda is of a decay constant, that is a plus b log r. Okay, so with a and b as a part constant, so according to part this law, the alpha particles emitted by the part element actually having larger disintegration constant have longer range, and vice versa actually. So those have the part larger means a larger disintegration constant, they have a very long range. Okay, and those have the long range, they have also part larger disintegration constant. Okay, so then you can find actually what this Georgia neutral law tells that the graph of the part log lambda mean decay constant versus long r is a part straight line with a slope b. This is the part the graph that is log lambda by a part log r actually. Okay, so here you can find uh, just you can find here this is the part relationship, and this lesson this is like a part equation of a part straight line. Okay, then okay, so where c and d are part simple constant. Okay, and if you can calculate actually this is the part relationship between the part this energy and also the part log means the relaxation time. This is but not but only that this lesson that you maybe remember, that log lambda and also that part log r. Okay, now I may part go to the part Gamo's theory of the part alpha decay, because this is a part long questions for you. So actually in 1928, G. Gamow, R. W. Gure and E. U. Cadden independently and nearly simultaneously provided an acceptable explanation of alpha decay. That means regarding the part alpha decay, this is the Gamo's, the first was explaining the part this alpha decay actually. Okay, so according to the part this alpha this Gamo's theory, that you can find it here, that the alpha particles are believed to be trapped inside the nucleus by Coulomb barrier in a basic form of this theory, but it is only has a small chance of existing the part nucleus. So they told actually they believe the alpha particle are simple trapped inside the part nucleus by the Coulomb barrier. Okay, and that is get a part a small chance to for existing the part nucleus. That means alpha particle, they assume that part the alpha particle never part emitted from this part nucleus, rather they get trapped. But the disintegration of the heavy nuclei reveals that two proton and neutron can occasionally group together to form a particle within the nucleus. So they think that part a heavy nuclei reveals that the two proton and the two neutrons can occasionally group and they can form a particle within the nucleus. The strong and the short range attractive nuclear forces must act on alpha particle when it is inside the part nucleus. However, it leaves the part nucleus and the Coulomb repulsion caused by the part remaining positive nucleus, that is Z minus 2e, and where Z is the part simple the charge of the part parent nucleus that of the alpha particle. So outside the part nucleus, Coulomb potential energy, that is at a distance r of alpha particle from the center of the nucleus, that is given by part this 2 into Z minus 2 whole square by 4 pi epsilon 0 r. Okay, and that you can find actually but this is the part you can see. So this is from 0 to r, this is a range, this is the part means just very periphery to the part nucleus actually, and after that we can find this interaction, the potential of the alpha particle simple goes on part decreasing here. So this is called the part Coulomb potential, and this is the part distance, this is the part energy, and this is the part that how a alpha decay actually part get emitted, that is the part schematically that is part get represented here. So this is called a potential well and Coulomb potential barrier in a nucleus, and the alpha particle wave function is oscillatory in part nature inside the part nucleus. You can see from 0 to r, that means from the center to that of a surface of the part nucleus, it is just oscillatory. Okay, so then you can find actually what this is the part this is the part idea that is provided by the part Gamos actually, And he also part mentioned the Coulomb potential given by the part this equation R, this equation that is where R is greater than R, VR describes that outside the part nucleus, and if we neglect the part recoil energy of the part daughter nucleus, the kinetic energy of the alpha particle asymptotically equal to part Q actually. So this was the part the theory that is proposed by the part Gamos. Okay. Now we can go to the part calculation of the part the Q value of a part this alpha particle. So let me go to the part this Q value of part calculation of the part alpha particle here actually. Okay. So just you can see I calculate the part this Q value here. Okay. So here, according to the Gamo's theory, actually, for that to explain the alpha particle, we can imagine in part moving it back and forth. As I told the part inside the part nucleus, this is it is found to be part simple oscillatory. So the particle may be part the alpha particle may with a speed v given by its kinetic energy that f is nearly equal to v by 2r. And similarly, the value of the part f for alpha particle is found to be part also this much here. And here you can find this is the part actually. Hello. Yes. Hello. Yes. I'm audible.
Yes, sir.
Okay. See here. So this is the part actually the total kinetic energy of the part alpha particle where given by the part twice n, and that is part q plus c, that is a part q value of the part energy that's we may calculate in part in beta decay. And this is the total q plus q is called the part total kinetic energy of the part alpha particle inside the part nucleus. Okay. So that you can find actually yes. So by treating part this is the part is total energy, and if you can create the barrier of the part the barrier means the where the part the alpha particle cannot but cross the part this nuclear energy. So a series of narrow rectangular barriers in one dimension, and assuming that the elements barrier height given below, that we can find the penetration probability is found to be twice square root of twice mq by h square, and here is equal to 2. This is the part potential of the part nucleus inside the part nucleus. Okay. And where that you can find the wave function of the each barrier given by the part square root of 2m. So these are all things I think that you may solve by solving the part Schrodinger's equation in a square wave potential. Okay. So this is similar to that of the this alpha particle decay, so similar to that of the part this solving the part Schrodinger's equation in part square wave potential here. Okay. Now you can find also the part the entire the as you calculate the part the reflection coefficient, and also you can calculate the part transmission coefficient. And if you have read about the part tunneling effect, that you can find this tunneling effect, the transmission probability is also for given by a to the power minus 2 into power r to b rdr. So where that is g that we can get this actually we define e to the power minus 2g. So t is called the part called the gamma factor, and that gamma factor can be calculated by part this all these part constant relation, the constant factors that is associated with the energy of the part alpha particle. Okay. So now coming to the combining part, these equations are 10 to 14 actually that we can find with the performance and probability. We can write an expression for alpha, and that decay constant that alpha is equal to p f e to the power minus 2g. And in order to estimate the dependence of the half-life on the part decay q value, okay, we take the U30 means uranium 238 as the parent nuclei, and you can calculate the penetratability factor. Okay, that are given by the part equation 14 here. This is called the part penetration or the tunneling if the tunneling penetration factor actually. Okay, and this is the part simple the gamma factors. Okay, that can be part get modified with this. We are omitting actually the steps because many steps that were given, then it is not possible to write all the part steps mathematically. So in the exam also that you can write also like that. Okay. Now so after that actually this is part numerical calculation not to be there. So here you can have a selection rule in alpha decay. So when the spin of the part initial and the final states differ, it can be shown that the alpha particle loses some of the part orbital angular momentum, which prevents the part emission, because in all the cases alpha decay is not possible. This there has to be obey some the selection rule. Okay. So there are two key elements that controls the part intensity variation. The first is the part simple states the part energy rises, and the second component which may affect the chance of perfect preformation is the structural variation between the part initial and the part final states. Now the effect caused by the particle losing a few unit of angular momentum, which is a part minimal in comparison to these two effect actually. So the parity of the part wave actually is given by part -1 to the power L, where L is the orbital angular momentum quantum number, and there is a parity selection creation for decay that depends upon the angular momentum. The parities of the part initial and the final nuclear states will differ if L odd and remain the part same if L is part even. So due to the part conversation of parity in alpha decay. As a result, this rule forbids some decay. For an example, if we can say oxygen flash, actually parent state cannot decay into the odd parity state when even spin or an even parity state with the odd spin. That means we can say alpha decay is but not possible from even. Rather, we can have a part even parity or odd parity, but not even odd or odd even. Okay. So this is the part, the selection rule that has to be part obeyed by the your alpha decay processes in a nuclear reaction. So particularly in this, we have read the part that's called the part these are means gamma state of alpha decay, and also the part q value already I have mentioned in the above that you can see. And okay, then I'm coming to part beta decay actually. So first of all, you should know what is beta decay, what happens in beta decay, types of part beta decay, q value of the beta decay, Newton hypothesis, like it is given in your first syllabus as beta decay. Okay, Fermi theory of beta decay that you have to see, then shape of the beta decay spectrum that has to be part read here. Okay, so let me part discuss only these factors actually. Okay, so here Fermi theory the beta decay, then Fermi Curie plot. Okay, and the parity, those all the things are part there. I may be part share all the things here. Actually, what is that part beta decay actually? Listen, beta decay is a part type of the part radioactive decay in which a proton is transferred into a neutron or vice versa inside the part nucleus of a radioactive sample. All of you see, it is a type of radioactive decay in which a proton is transferred into a neutron. Okay, the processes like beta decay and alpha decay allow the nucleus of the radioactive sample to get as close as possible to optimum neutron or proton ratio. While doing so, the nucleus emits a beta particle which can either be an electron or positron. Okay, so remember in a beta decay, we are just emitting a part alpha particle, sorry, a electron. Okay, or that is maybe you can get a by transfer of a proton into a part neutron or vice versa. Then what happens in a beta decay? When beta decay is a radioactive decay in which a beta ray emitted, beta ray means electrons is emitted from an atomic nucleus, and during the part beta decay, the proton in the nucleus is transferred into a part neutron and vice versa. If a proton is converted into a neutron, it is known as beta plus. Similarly, if a neutron is converted into proton, it is known as part beta minus. So accordingly, beta decay two type. One is beta plus and the other is part beta minus. Okay. Remember, when proton is converted into neutron, means a positive converted into part neutron, it is called beta plus. And similarly, when a neutron is converted into a proton, it is called part beta minus actually. Okay. So due to the change in the change in the part nucleus, a beta particle is emitted, and the beta particle is a high speed electron when it is a beta decay, beta minus decay. Okay, and a positron when it is a part beta plus decay. Beta particles are used to treat health conditions such as eye and bone cancer, and also used as a part tracers. So these are the part some of the applications where you can use a part beta decay. So for example, you can see carbon 610 when you can convert it to boron 510 with the emission of a part beta plus. Okay. Then the types of part beta decay you can see beta minus and beta plus. So beta minus decay already I have told you here. When a simple neutron is converted into part a proton, that's a part beta minus. Okay, and this is you can see a proton, that neutron is converted to proton and electron and a part anti-neutrino. So this is a part beta minus decay. Similarly, beta plus decay you can find when a proton is converted neutron into electron plus or positron and also part neutrino, then that is called the part beta plus decay actually. Okay, and this is the part an example, the schematic presentation you can see beta minus decay and beta plus decay that you can see here clearly. Okay, now we can talk about the part q value in the part beta decay. In a nuclear and the particle physics, the energetic of a nuclear reaction is simply determined by the part q value of that reaction, And the Q value of the part reaction is simply defined as the difference between the sum of the part rest mass of the part initial reactant and the sum of the part masses and of the final product in energy unit. Okay, so if we consider a typical reaction in which the projectile A and the target A gives place two product, that is B and B. Okay, and this can also be expressed in notation, that is A plus A gives rise to part B plus B over in a part more compact notation, that is A of A means A will react with the part A gives rise to a part a product, a daughter nuclei, and also part product nuclei. So the Q value of the part reaction is simple given by part the total energy released in the part reactant side minus the part product side minus reactant side, that is called the part Q value. You can see MA, mass of the part small particle A, then plus mass of the particle A minus of the part mass of the particle product nuclei and also the daughter nuclei into C square, that as per the part binding energy relation. Okay, so so this is the part, the total process of the part Q value or the Q value of the beta decay, that is part represented in a schematic way. Okay, now, if you can come to the part, actually the part this neutrino hypothesis of the part beta decay actually. So here you can find actually part this Paulis in 1930 deposited means postulated the part existence of a new particle called neutrino hypothesis, and that is emitted by that is actually compelled by the part beta decay process. And this new particle carries away an amount of energy equal to the difference between the observed beta particle energy and the endpoint energy, that is R of the continuous spectrum, in order to satisfy the conservation of energy. So there can be three ways of the part energy sharing between the beta particle and neutrino as mentioned below. So beta particle can be the part maximum energy, that is E max, and neutrino can be zero energy, that is the part zero actually. Similarly, beta particle carrying some medium energy is less than E max, and the neutrino carrying low energy, that is a part E beta. So E beta plus your part EV, that is the part total part the total energy or maximum energy, and beta particle with very low energy and neutrino carrying maximum energy, so that we can find E beta plus E neutrino, that is equal to part E max. Now, in order to satisfy the part conservation of the angular momentum, charge, and the nuclear statistics, the following properties are assigned to the part neutrino. Just like we can say neutrino has zero charge and hence negligible magnetic moment. The mass of the neutrino is zero and almost zero. Neutrino has a spin of the half. Neutrino must be a part fermion in order to obey nuclear part statistics. Okay, so this is the part, the total, that is a schematic representation of the part neutrino hypothesis or beta decay here. Okay, now we'll discuss actually Fermi's theory of the part beta decay. Okay, so here you can find that so what is the Fermi theory? So according to the Fermi theory, the electron and the neutrons are actually produced during the process of a particle alpha particle as a beta particle emission. So keeping these things in the mind, the electron is created but not present in the nucleus. Okay, you see the electron inside is not present, but it is a part inside the part. You can see it is a part the it is created actually, and that creation of the per beta particle actually gives rise to per beta decay. So the neutron is also referred to as a particle, that is Barth partner, and the basic concept in order to use the perturbation theory. Okay, so Fermi's hypothesis require that the interaction responsible for beta decay process is part weak, okay, and not to be part strong. So it is a part weak interaction. The Hamiltonian that causes the part decay provides the formula for the transition rate between the part initial and the part final states in quantum mechanics. Okay, and for which we have the part the Fermi golden rule. If you have read in part quantum mechanics, this is the Fermi golden rule for the part beta decay, that dfi means dwfi. Okay, final and initial, the 2 pi h cross, and this is the part the Hamiltonian probability, that is f s omega w I mod square rho e. Okay, and the expression for the density state is given by part rho is equal to dn by part de actually. Okay, so if you can just go to the part detail, then you can understand actually the part the Fermi theory, the part beta decay. Okay, now we are just calculating the part is probability density and also the part probability density of the particle, the energy of the particle, the density of the particle, and that the total energy density of the particle with the part variation of the part energy. This is the part the things that you may follow with your part systematic part derivations that I provided here. Okay, then Another is part there actually, part important curve is there, that is called this is there or not, let me see actually. Okay, so this is called the part for me, yes, we call it actually Fermi Curie plot actually. So to give you a detailed discussion to the part this beta decay, that Fermi Curie actually have provided a graph or plotted the part data, and he observed that this is a part simple linear variation, okay, and that you can find actually part this the total probability which is for always constant, okay, and this function is called the part Curie function part k, so that I can part k is equal to part this much actually. So now if you can plot a part and the graph between the k versus a part this dw means part this total probability, then you can find this is just like a part simple but a curve like sorry a graph. Initially it is goes on per increasing, then after the part maximum energy it is goes on per decreasing. So this two endpoint actually for 0 point energy, and that is called the part the maximum endpoint energy is called part Emax actually. Okay, so that is the part nature, and that is also the part the Curie plot, that is k plotted versus the part you can find with the part energy actually here. Okay, so this is the part a long question that you can see in beta decay. Similarly, in the part gamma decay, you can also find. Yes. So here you can find also part in gamma decay. Okay. See, so what is gamma decay? Then part gamma decay, you may get it part in a part a short note actually. It's not, but alpha decay and beta decay very important. So see here, what is that gamma decay? So as I previously told you part when the alpha particle or a helium, that is 2 helium 4 plus will emitted, that is alpha. But when the electron is per simple emitted with a part minus and also plus the electron positron, then that is called beta. But similarly, you can find a part gamma decay where you can find a gamma particle is actually part released when there is a decay. We can say that is called the part your part gamma decay actually. Okay, so then you can find actually this just you can see here. So gamma decay or gamma decay simply represents the disintegration of a part parent nucleus to a part daughter through gamma ray. Okay, just if this is a part parent nucleus, we can get a part. You can see this is a gamma ray, because you know part gamma rays are part not having part, the 0 0 means atomic number 0, mass number 0, and this is part same as that of the part parent nucleus with a part emission of a part photon simple. Okay, as you can see, if a nucleus emits a gamma ray, atomic and mass number of the daughter nucleus remain same. Okay, but the daughter nucleus will form a different energy state of the same element. That means this is the daughter nucleus, it has the part same energy level as that of the part parent nucleus. Okay, so then you can find this is the part actually gamma decay that happens. So if we can say actually part this is a part one of the part let to the part particle, it's have a part means you can say let it be part Zenon. Okay, 54 131, and you can see that 131 when it will be part emitted in the higher excited state, it will be emitted the part gamma means a photon, and by reducing or emitting that photon it can be come to a part stable state actually. And these are the part different states of the excited states of the part this gamma decay actually. Okay, so this is gamma decay or decay scheme of a part iodine means it a halogen group of the part element, that is 131. Okay, in most practical laboratory sources the excited nuclear states are created in the decay of a parent radionuclide. Therefore, gamma decay typically accomplishes other form of decay such as alpha or beta decay. After a beta decay, nuclei usually contains too much energy to be in the part in the final stable or daughter state. So gamma rays are part high energy photons with a very short wavelength and thus very high frequency actually. You know, gamma rays are actually used in part many cases actually part for the treatment of the cancer. So that gamma radiations actually is a part is a big deal for the part this part nuclear part decay processes. Okay, so gamma rays from the radioactive decay are the part energy range from the part some keV to part some MeV and correspond to part typical energy level. Okay, in which in the part nuclear you can find with a reasonable long lifetime as observed actually. Okay, so this is the part, the gamma decay. Then if you can composition of the part, scattering of the part gamma ray, we are just uh, uh, you can see actually for the detailed theory that I have mentioned here. Okay, so this is the first schematic reference of our gamma decay. You can see this is the first response of a part nucleon. We are just bombarding a photon. So the photon energy of the response is m0c square. This is a particle. The photon is a part, this electron at rest actually. So it is undergo the part Compton scattering, the emission of a part gamma particle. Okay. So this is called the Compton scattering diagram. Okay. So that if you just if you have read the part in a base level, that is Compton scattering, the same things that we have written, only but here calculate the part energy of the part is particle. Everything that is there, you can go to the part of this mathematics, and finally you can calculate the part total momentum before and total momentum after. So then you can find that is found to be part remain conserved actually. So these are all things are part there that you may go to the part this mathematics actually. Okay, so now one thing is part there you can find, that is part pair production. Okay, so here you can see yes, already I have already discussed the part parity valuation for beta decay. Okay, and also the part selection rule that I already part discussed. Then the pair production and the part annihilation. As already I have told you, part when a gamma decay or when gamma decay takes place, it also part responsible for the creation and annihilation of the part a proton and a proton that is a positron and a part electron. So that pair of the positron and part electron, we call it actually a part that is called your part the creation or a pair creation and annihilation. Okay, so this maybe you have also part read in the part in a graduation level. It's a part theory that I can say here. Okay, then you have the part actually uh, other things are part there. Let me part take these are not in the part in your part course. Okay, okay, so this is all about the part gamma decay. It is a very part, a very short means what I want to say means a short note that you can find in the part in your exam actually. Okay, now I'm coming to the part actually the nuclear reactions. Okay, so in nuclear reaction you have actually direct and compound nuclear reaction mechanism, compound nucleus, reciprocal theorem, Britt-Winger formula, resonance scattering, all things are part there. Just you can see how much you can complete it here today. You can see, otherwise I can share the part these notes to you, all of you. Okay, just you can see. So you all of you know a nuclear reaction is a part such a reaction so which involves a parent nucleus, that the parent nucleus actually part get bombarded by a part incoming or a part target. So that means a target nucleus is bombarded by a part incoming a part neutron, which will be part on breaking or splitting, that gives a product nucleus, daughter nuclei, and some energy to be part released. Just you can see, suppose that a 2 helium dot alpha particle, I bombarding a part nitrogen, I am getting a part simple unstable nucleus iron 9, 18, and okay, and which on, and since it's unstable, it can give rise to a part oxygen 817 plus 1H1. So this is a part target nucleus, this is a part incoming nucleus, this is a part unstable nucleus, this is a part product nucleus, and this is a part daughter nucleus. So this is called the part, you can see this is called the part compound nucleus, and that compound nucleus is very, very unstable, means due to its high energy. Okay. In general, a nuclear reaction can be represented by, you can see just I have written ZXA plus X gives rise to ZYA plus Y, or in compact notation, it can be written as part X, okay, X or XYY. Okay. So this is a part in a compact reaction representation, and this is a part explicitly reaction. Okay. Now
Excuse me,
you
sir.
can, yes, yes, yes. Tell me.
Sir, in the first reaction, there is a F. Fluorine, that is Fe, iron.
Priyasini, actually, I'm not getting. Please tell me again.
In first reaction, sir, there is F. F
Yeah,
means
okay.
that is
Yes, yes, yes,
fluorine, no?
yes, yes. Let me tell. Yes, let me tell. You can see. See. So what we're actually tell me again.
Sir, in reaction one, in
So
that reaction, F is there. You told sir
Okay,
that it's
this
iron.
X, this small X, so the small X, so
F.
F.
Yes sir. That is iron or that is
Okay,
fluorine.
this is fluorine. This
Yes
is
sir.
fluorine here, not
Okay
iron.
sir.
This is fluorine. You see, this is
Sir,
nitrogen, na?
you told that that is iron.
No. Fluorine, not iron.
Yes sir.
Okay, this is fluorine. If you have remembered the part, actually the part atomic number, this is iron is for something Fe shape. This is not iron, it's fluorine. Okay. If this may be mistake, that's maybe fluorine. Okay. So you are asking that one, na?
Yes sir. Thank you sir.
Okay, thanks. So just you can see actually, so we are dividing actually the part nuclear reaction different type. One is part elastic scattering, and it is a part simple process. You know that in a elastic process means both the energy and the part momentums are get conserved actually. So it is in process in which the incident and the part outgoing particle are the same, and the kinetic energy part simple conserved actually. So when the kinetic energy get conserved, now we can say this is a part elastic scattering. Thus, if the incident particle and the target nuclei are simply scattered by each other without any change in their relative energy, the process is said to be part elastic scattering. Okay. If the incident particle is dominated by part A and the target nuclei by X, then the elastic scattering and may be part systematically represented as part. You can see this is A plus X gives rise to X plus A. You can see there is nothing is energy is not changed, just only we have interchange. So for an example, you can write one electron when bombarded with a part carbon 612 that you can get 6 carbon 12. So this represents a part simply part elastic scattering. Similarly, when nitrogen is also part bombarded with a part uranium, then you can get also part the same uranium with the part neutron particle. Okay, these all are part simple elastic scattering. Sometimes you can also part write that pi minus plus gives rise to n plus a part pi 0. Okay. So inelastic scattering that you can find, the bombardment process may result into part change in the part relative energy without the change in the part internal structure of the target nucleus, and this type of process is known as a part inelastic scattering. And it is in the although the incident and the outgoing particle are the same, but kinetic energy is part not conserved during the part process. Okay, you see, inelastic scattering there is kinetic energy part not conserved, but in elastic scattering kinetic is conserved. So in this process, actually the target nucleus after the interaction is not left in its initial state, but it is raised to the excited state. It is not actually means it is not actually the raised means it is not to be excited more, rather it is only to be part having energy is part increases and to be in a stable condition. Okay, lower than that of the incident particle by an amount equal that of the excited energy given by the part target nucleus. And symbolically I can say that initial scattering is part A plus X gives rise to X star. So star means it is a part simple unstable, okay, plus your part A. And these are the part some of the examples that is given for inelastic scattering. Then nuclear reaction I already part described to here. So this is the part symbolic representation. So what is the nuclear reaction I told? Then this is a part symbolic representation, and this is a part simple example, and very compact form. This can be represented as part X, A, B, Y. So X is the target, A be the incoming particle, B is the outgoing particle, and Y be the part daughter nuclei. Okay. So this is the part a symbolic or the compact presentation of the part this nuclear reaction here. Okay. Now the study of the part nuclear reaction actually involves the measurement of the following quantities, just like intensity, energy, and identity of the part incident beam particles, and the number of particles which are emitted from the target per unit time, and the energy and identity of the part emitted particles are of the part residual nucleus. Okay, this is the part the basic part factors or the nuclear reaction involves the part this measurement in a particular nuclear reaction actually. Okay. Now, I can say actually for this induced activity of the product nucleus if any type, then just have it is a particular or a typical equations, and using that typical reactions that we can calculate the part the total energy of the details about the part this nuclear reactions. You may part go through the detail. Okay, so after that I may be part go to the part this conservation law for the part nuclear reaction. You know, so as I have told the part there is a target nucleus, there is an incoming nucleus, there is a product nucleus, there is a part daughter nucleus. So naturally they satisfy some conservation of energy like conservation of the part electric charge you can say. Similar concept electric charge, conservation of part neutron, okay, and the conservation of the constant of motion of classical and quantum. This is not required, but only conservation of the part nucleons and conservation of charge that you should know, and this is written that you can read there. Okay, so now the charged particle induced nuclear reaction also. Just I'm not going to the details of this. This is may not be, but you can see when there is some of the nuclear reactions that takes place by induced of the some particle. So it may be also for different type of nuclear reaction, that is P alpha. So P alpha reaction means P is a per incoming particle proton and alpha is a per outgoing particle. So for example, you can see proton. So ZXA plus 1H1, this is gives us to Z plus 1, means when this part reaction takes place, so the atomic number get added, and similarly the mass is also part get added, they form a compound nucleus, and from that compound nucleus that which particle is emitted, accordingly that product nucleus that you can find actually here. So you can see Z plus 1, C, A plus 1, and that after the part emission, you can find Z minus 1, Y, A minus 3 plus 2 helium 4 actually. Okay. So now, if we collect for this type of reaction has a status of being the first artificially induced reaction studied by Walton and Cook-Croft in 1932. So in this reaction studied by Walton and Cook-Croft, lithium 37 target was bombarded by means of 0.7 MeV proton to product 2 alpha particle as follows. So this is the part A reactions, that is actually the typical reactions which was first observed in by this Walton and part Cook-Croft. Okay. So there are part also many examples are given. So this is P alpha, this is P neutron. You can see this is P gamma reaction, this is P deuteron reaction. Okay. So these are the many reactions are there. You may read in the details actually, or these are maybe some of the nuclear reactions which may find in the exam. To complete the part nuclear reaction by practicing this, you can get it actually. Okay. So now we can go to the part. So you can go to this detail actually of this. Then the photo distance part not in a part in the syllabus actually. You have only yes yes. I've just part completed here conservation laws. Okay, mechanism that I've all told you. Okay, so now we can go to the Q value, already Q value that not this is but not required here. I've just written actually because this is a non-relativistic Q value equation. You may also put it there. Okay. Okay. So here you can once you can calculate the binding energy and the part Q value of the part nuclear reaction. So as like the part previously you calculate the part mass defect and also that calculate binding energy, the same way we calculate the part it here. You may get one questions also part of the part nuclear reaction. But basically the questions is coming. I have written the part questions actually. You can see here. Okay. Just you can see one thing I have to complete. I have to tell the nuclear reaction cross section, or that is part scattering cross section. So this is also part one important. Okay. See, this we all know that part for all type of nuclear reaction, certain conservation laws that you have seen, law of conservation of the part energy and also the nucleons are satisfied. It is very difficult task to ascertain whether the particular projectile will initiate a particular nuclear process or not, but somehow we can predict the or we calculate the part, we are able to calculate the part this nuclear scattering cross section. So how can you calculate the part nuclear scattering cross section? All of you see. So sigma is equal to number of given types of event per unit time per nucleus by the number of projectile particle per unit area per unit time actually. You can see the given type of events per unit time per nucleus by number of projectile particle per unit area per unit time. So this simple ratio gives rise to the first scattering cross section actually. Okay. So the total scattering cross section is due to scattering as well as also for absorption. Okay. So and this is the for the line level width. So which you may calculate by this is for simple constant which is given by the h plus lambda. Lambda is a part decay constant. Okay. And this is the part uncertain principle which may be also satisfied by scattering cross section here. Okay. Now these are the part you can see some of the example also for given. This example you may find as a problem in your part in your nuclear physics. Okay, this are already part done. You can go for part, just check it actually. Okay, I'll share this part this to you. Okay. So almost but all this part reactions mechanism I've already part discussed here. There is you may read these things and in addition to the part your material provided by the part your igno. Hmm. And it's just in the summary or there is a part some questions also I may part provide to you. Okay, just like the describe the type of nuclear reaction with the suitable examples, explain the part conservation laws of our nuclear reactions with the examples. Okay, discriminate between different charge particle in induced nuclear reactions like alpha p, alpha n, so alpha d. This reaction you have distinguished. Okay, there is a part actually for deriving expression for the Q value of the part nuclear reaction. You may do that one. Okay, so this is the part things that we cover in the part in nuclear part reactions here. Okay, so only one module is for there. I have to be just that is elementary particle. So in one class I may complete in part this elementary particle or there is some questions I may provide there. Okay, hello, yes.
Yes, sir.
In one class I can give the part actually because all of you I'm telling to just the last part actually you can attend and many questions you can get from the part last part that is a particle physics. So this particle physics I will be do it part in a very nice way or I may provide all the details of this particle physics. So you may just consult to the part the study center and there may be only one class I need within the 2 hours I may complete that part actually. Okay, hello.
Yes, sir. Yes, sir.
So I'll share all this per detail to all to you, and then you can share to the others. Okay.
Okay, sir.
Yes,
Okay.
sir.
Okay.
Sir, tomorrow I will not.
So tomorrow you can do the class.
Uh,
Yes, sir.
yes, sir.
So if you then I can complete this course actually.
Sir, all the materials you will be provided sent.
Hmm?
All the materials you will send, sir. Yesterday you didn't send, no?
Yes,
So
yes, I can share the matter. Don't worry. But the thing
okay,
is,
sir.
but there actually, so if the just if you have one class, then we may be. But actually, tomorrow I may complete it actually.
Okay, tomorrow block three is there, particle physics. Yes, sir.
So what's the action?
Block three means in our study material it is block three, particle physics.
Particle piece I will complete it tomorrow.
And that is from unit 11 to unit 15. Yes, sir.
Yes, Priyadarshini, I'm not getting actually. This is very.
That block 3 is unit 11 to unit 15 means last block uh, in our nuclear physics.
Okay. Hello.
Yes, sir. Particle physics that is in block 3. I told like that only.
Yes, 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 yes. It is in plus three.
In that block 3, unit 11 to unit 15 is there. So tomorrow we will learn this.
Tomorrow if you want, so tomorrow you will do the class, though.
Yes, sir.
Okay, okay, then no problem.
The timing is 6:30 or 7, sir.
You may join from 6:30.
Okay, sir.
Okay. So let me tell to the center. Okay. Okay. Let me leave now. Okay.
Okay, sir. Thank you.
Okay. Thank you.
Thank you, sir.